Hello all, let's start part 2 of our lecture for section 3.3. If you remember from previous lecture, I talked about how to find the standard deviation of a sample, and the last thing that we did, we talked about how to find the standard deviation for a population, which the formula was sigma equals the square root of x minus mu square over n, correct? Another topic that's really close, has a close relation with the standard deviation is variance, correct? I will not give you a new formula, don't worry. How to find the variance, correct? We will talk it right now about variance of a sample or maybe population. First of all, what is variance? Correct? The variance of a set of data is a measure of variation equal to the square of the standard deviation, to the square of standard deviation. This part is important. Equal to the standard of standard deviation. Look, for the sample, S was your standard deviation for what? For sample. If I want to find variance, correct? If I want to find sample variance, after I found the standard deviation, I will just square it. As a square, will be your variance, correct? And for population, lowercase sigma was your standard deviation. Now, population variance will be sigma square. For example, you see in this example, the examples that we did, I found the standard deviation of that bank wait time 477. You found that 1.773, but actually it was radical 3, correct? If they tell you find the variance for that example, which your S, for example, for this, your S is radical 3. They are asking you to find the variance. What you do, you find S square. S square equals means square this side, radical 3 square, which gives you what? 3. Or for the other examples that we had, sigma equals the square root of 49, correct? Or 7. If you want to find the variance for that, you can say sigma square equals the square root of 49 square, and these two cancels out. It means it's 49. That easy, correct? There is no new formula for variance. What you do, you calculate your standard deviation, and after you found your answer, square it. That gives you what? The variance. Now, some more properties for a standard deviation, correct? Properties of standard deviation. Number one, closely grouped data, closely group data will have a small standard deviation. Let me explain what does it mean. I'll go back up to show you an example. Look at here in this example. Our data is 477. They are really closely grouped. There is not much difference between 4 and 7, right? They are really closely grouped. When they are really closely grouped, look at here, your standard deviation is 1.73. It's really small, correct? But if you come to this example, which my data is 1, 3, 14. You see here, 1, 3, 14. They are not closely grouped. Where is 1? Where is 14? Where is 3? They are not closely grouped. What happened? Your standard deviation was what? Bigger, 7. Then it's true. The first property is true. If your data closely grouped, your standard deviation is what? Really small. And the other one I can say, separate out data will have a large standard deviation. And you see both of them already in example, a large standard deviation. If your data is really closely grouped, always it gives you a small standard deviation. If they are separated, you have a separated data, then in this case, your standard deviation will be large, correct? Another note here that I want to put for you, if a data set is normally distributed, we can use the, I'll put 2 dots here and I'll go on the other and new line, empirical rule, correct? But remember this, I'll underline it. If your data is normally distributed, only and only if your data is normally distributed. What does it mean? It means your graph is a bell shape like this, correct? You get a bell-shaped graph and your mean is usually here, x bar or mu, whatever you use. If it's population mu, if it's a standard deviation, it's x, if it's a sample, x bar, correct? If your data is normally distributed, again, I'm telling you only and only if your data is normally distributed, you can use this rule, which we call it empirical rule. What this rule talks about? Few things, few notes. Note number 1, 68% of data will fall within one standard deviation. Now, I'll show you in a diagram also here. This is your normal distribution, correct? I'll grab something like as a normal distribution. Let's think it's a normal distribution, and let's talk about sample. Here you have X bar. If your data is normally distributed, 68% of the data will fall within one standard deviation. Remember the definition for a standard deviation. I told you to just focus, try to understand what does it mean. Standard deviation is actually the distance of your data from what? From the mean, correct? This is the distance of the data from the mean. If I call this S, correct? If your standard deviation is only one away from the mean on the left side and also here on the right side, correct? It means this area, if I show the area for you, and this area, which is a topic of calculus, we cannot explain it too much here because this is the area under the curve, right? But they calculated, they put as a rule here for you, 68% of your data will be in this region, one standard away from the mean, correct? When your data will fall within one standard deviation away from the mean, 68% of your data will be in that region, correct? Star number 2. 95% of data will fall within two standard deviation. If I show it in a graph for you, in a better graph, for example, this is your normal distribution. Here is X bar, our mean, correct? Here, one standard deviation, the notation will be X plus what? X bar plus S, one standard deviation away. And on this side, this one will be X bar minus S. Now, when you come to this point, two standard deviation away, correct? This one is actually X bar plus 2S, two standard deviation. And this side will be X bar minus what? 2S. If your data falls in this region, like this much, this is actually 95% of the data. Correct? Number 3. 99.7% of the data will fall within 3 standard deviation. Correct? I will just show the 3 of them. This is your normal distribution. For example, this is your X bar. If I mark here as a X bar plus 3S, 3 standard deviation, and here X bar minus 3S, correct? This area actually represents for you 99.7% of the data will be in this region. Later we will discuss where we use this, and maybe after this I'll do a few examples, but in 3.4 you will see we will actually talk about z-score there, and you know Why we are using this? We are using to compare different datas, correct? But before even going to example, some more notes for you. If a data or if a data value, let's make it better, if a data value lies within two standard deviation of the mean, it's considered usual. For example, I'll just show in a line for you. This is your x bar, and here it's x bar plus 2s, 2 standard deviation, right? And here x bar minus 2s. If your data falls within inside up to 2 standard deviation, you call this data usual, correct? Note number 2. A data value outside of 3 standard deviation, outside 3 standard deviation from the mean is very rare. It's not going to happen, it's rare, correct? Soon I will do an example. For example, did you ever hear that someone is like 10 feet tall? If I talk about height of the people, 10 feet. Oh, I heard about 8 feet. I saw 2 feet tall also. But 10 feet or 12 feet tall, no. If there is one, it will be rarely rare, correct? Because if I show it here, the average maybe mean of the height is usually for us 65 maybe inches, right? Many people they're in 65 inches, which is 5'5", 5'6", 5'9", 5'10", 5'12". These are kind of the data that we get if we want to find talk about the height. But if something is out of this, x bar plus 3s or x bar minus 3s, correct? Something here, if I mark it with the red, for example, I told you 12 feet tall, it will be out of the range, correct? We call, or 2 feet tall, correct? These are rare data that you can get, correct? This note is about this. Now, I'll make an example. It's not a correct data, it's just an example. We are talking about a sample, first of all. Why I'm writing here sample? That I want you to use the correct formula. Sample. Heights are normally distributed with the mean of with a mean of 65 inch, which is what? 5.5. 65 inch means 5.5, correct? And a standard deviation of 3 inches. Correct? In this example, we are focusing to see, to just graph and see how much is the 1 standard deviation away from this mean, how much is the 2 standard deviation away from the mean, which heights, right, are working that way, correct? Let's graph it. Let's graph a normal distribution first. Something like this. I'm trying to do a good graph. I will put the mean here, which is given to me, 65 inches, my mean. Standard deviation of 3. Now, if I ask you what will be or how high will be 1 standard deviation away on the right side of the mean, and what will be the height of the people that they are 1 standard deviation away on the left side. Your formula was x bar plus s to the right for 1 standard deviation, which means 65 plus 3, which gives you 68, correct? It means 1 standard deviation away on the right gives you 68 inches. 1 standard deviation away on the left, because your formula is x bar minus s, then it will be 65 minus 3 will give you what? 62 inches. It means here I have 62 inches, 1 standard deviation away. Here I have, if I erase this part to come right there, here I have 68 inches. It means, and 68%, when you are 1 standard deviation away from the mean, it's your 68% of your data, correct? It means somehow 68% of my sample, I don't know how much was that sample, couple hundred people maybe, right? 68% of them, they have the height of 62 inches to where? To 68 inches. Correct? Now, if you want to calculate 2 standard deviation away, correct? Again, this is my graph. Here is the mean, which is 65. I want to calculate 2 standard deviation away on the left, 2 standard deviation away on the right. Here will be 65 plus 2s. It means 2 times 3, correct? Which gives you 65 plus 6, which gives you what? 71. 2 standard. This was your formula, right? X bar plus 2s and x bar minus 2s. On this side, it will be 65 minus 2 times 3, which gives you 65 minus 6, which gives you what? 59. It means 95% of your data will fall in this region. And if you go to 3 standard deviation, it's the same calculation. You will add 65 plus 3s, 65 minus 3s. It gives you 99.7% of the data. Correct? One more example. Mean is 34 pound, standard deviation 8 pound. What percent of data will fall between 10 pound and 58 pound? Correct? I will just simply draw a line, even not show the graph, the actual graph. Your mean is given to you, right? Your mean is 34 pound. It's about the weight of the people, right? And your standard deviation is 8, correct? Now, what percent of data will fall between 10 pound, which is somewhere here, correct? And 58 pound, which is on this side. To find that percentage, you have to first find how far 58 is from 34 and how far is 10 from 34. It means you have to find what? Standard deviation, correct? This is your x bar, this is x, and this is x. To calculate that, you have to first find x minus x bar, right? This distance, you have to calculate first this distance. How much is this distance? And the formula is x minus x bar, right? It means 58 minus 34, which gives you 24. 24, 34, 60, 58, okay, 24, correct? This distance is actually 24. Now, how much is my standard deviation? My standard deviation is 8 pound. You want to see that how many times 8 goes to 24. It's a division problem, correct? It means you are doing this. You divide 24 by 8, which gives you 3. It means 58 is 3 standard deviation away from what? From the mean. Some students go this way. They add 8 on the 34, which gives you 42. They add another 8 on the 42, which gives you 50. Another 8 gives you, oh, 3 standard deviation away. But the easy calculation is to find the distance, divide by what? Divide by your standard deviation. That means if I create a little bit of formula, that in next lecture I'll name this formula for you, x minus x bar divided by s. That is actually the way to find the given data, how far your given data is from the mean, correct? Same way, if you calculate this side, x minus x bar, it means 10 minus 34 divided by s, or divide by 8, correct? Which gives you negative 24 over what? Over 8, which gives you negative 3, correct? Negative 3, the distance is not negative, but you know negative 3 means on the left side of the mean. It means you are 3 standard deviation away from the mean on the left side, 3 standard deviation away on the right side. Then you can say, when I'm 3 standard deviation away from the mean, 99.7% of the data will fall. It's good to write a sentence, will fall within 10 pound and 58 pound. 58 pound. Very easy example, correct? Last part of that lecture. Look, if I want to compare two different set of data with each other. In the first example, we talk about height, right? In the second example, we talk about weight of the people, right? For this one, for the first one, X bar was 65 inches. And for the second one was what? 100 and something? Or the mean was, in the second example, what was the mean for the weight? Let's say, for example, the mean for the weight is, let me create something, 175 pounds, correct? Your standard deviation is for this one 3 inches. Let's say the standard deviation for this one is 4 pounds. If I ask you a question that in which example the variation is larger, in the height or in the weight, looking to this table, in which data set or in which example we have a larger variation, looking to this table, your answer should be, we cannot talk about. We can't understand, we can't find if the height, which is with a standard deviation of 3 inches, has more variation than the weight, or the weight has more variation than the height, because here you are talking about inches, here you are talking about pound. How you can compare them where you have more variation? It's impossible. The only way that you can compare two totally different set of data, for time being, I'll give you something by name coefficient of variation. When you find the coefficient of variation, then it's really easy to compare your data. What is coefficient of variation? Actually, you are changing your variation to what? To percentage. And the formula is very simple. If I name coefficient of variation, CV is equal S divided by X bar, your mean or mu, whatever you use, times what? Times 100%. In the first example, if I want to calculate here, it will be 3 over 65 times 100, which you will end up with 4.6%. In the second one, if I calculate, it will be 4 over 175, correct, times 100%, correct, which gives you 2.3%. Now you can talk which one has more variation. Your first example has more variation because it's 4.6. This number is larger. Here you have 2.3. This number is smaller. You can talk about variation of two different data sets only and only when you are looking to the coefficient of variation. You have to change it first to percentage, then you can talk. Other than that, you cannot compare to different set of data. In this section, next section, I will talk in 3.4 about the z-score, which z-score is really gives you the power to compare different data, correct? To compare data measures between or within data sets, correct? I will stop the lecture here. See you all in section 3.4.